The last topic in this section is actually a really important one, and it's a calculation we're going to come back to again and again in later chapters as well. So we will see it again, but it's a good idea to start to understand it now. And it's called the standard score or the Z-score. When you know the mean and standard deviation of a data set, you can measure the position of an entry in the data set with a standard score or a Z-score. The standard score or Z-score represents the number of standard deviations a value X lies from the mean. So it tells you how far away from the mean is that data point in reference to the standard deviation. Usually we say Z-score, so you can use the word standard score as well, but you're going to hear me mostly just say Z-score in class. That tends to be more formal. And we do use a little Z there to show that we have a Z-score. So what you do is you take your value, so this is your data point, and you subtract it with the mean, and you divide it by the standard deviation. Now, here we're using the population mean and standard deviation, but the same formula also holds if you had sample data, theoretically speaking, right? So it's the same idea. Now, a Z-score, or we're going to do some examples in just a minute, can be negative, positive, or 0. When a Z-score is negative, it means that the data point lies to the left of the mean. So the X value or the data point is on the left of the mean. It's less than the mean. When it's positive, it means that the X value, so the data point, lies to the right of the mean. So it's more than the mean. If your Z-score is 0, which is rare, but if it's 0, it means the X value is exactly the mean. So the data point you have is the mean. So when you subtract, you get that 0 in the numerator. When the distribution is approximately bell-shaped, we learn from the empirical rule that about 95% of its data lies within 2 standard deviations of the mean. So when we transform the values to Z-scores, this means that most Z-scores should fall between -2 and 2. Remember, the Z-score represents the standard deviation for that data point, like how many standard deviations it is from the mean. So most data is within 2 standard deviations of the mean, so your Z-scores are going to be between -2 and +2 in general. If it's outside this range, which happens 5% of the time, it's considered unusual. A Z-score less than 3 or greater than 3 would be very unusual. It only occurs 0.3% of the time. So again, this is the idea that it would be more than 3 standard deviations from the mean. So your Z-score, again, tells you how many standard deviations that data point is from the mean. Let's do some examples. So the mean speed of vehicles along a stretch of highway is 56 miles per hour, and the standard deviation is 4 miles per hour. We are going to assume that speeds are approximately bell-shaped. So when we do Z-scores, we're using that bell or that normal curve. So we're going to have to assume that our distribution is normal right now. We measure the speeds of 3 cars traveling down this road. One went 62 miles per hour, one went 47 miles per hour, and one went 56 miles per hour. And you want to find the Z-score that corresponds to each speed. Okay, so the first thing I have here is I do know that my mean is equal to 56 miles per hour, and my standard deviation is equal to 4 miles per hour. My first car is traveling 62 miles per hour, my second car 47, and my third car 56. Now I'm going to find the Z-score for each case. So if you need to, we can go back to that formula just to review it one more time. So we're going to take our X value and subtract it with the mean and divide it by the standard deviation. So for this first group, I'm going to have 62 minus 56 and divide that by 4. For my second group, I'm going to have 47 minus 56 and divide that by 4. And for my last piece, I'm going to have 56 minus 56 and divide that by 4. It is very important that you start with the x value or the data point and subtract the mean, or else your signs may be off. So for the first value here, I have 62 minus 56. So that's, let's see, 4, 5, 6. So 6 over 4. Now, we do write our z-scores with 2 decimal places. That's pretty standard. Sometimes we'll use 3 decimal places, so there's a couple exceptions there, but usually we use 2 decimal places most of the time. Now, let's see, for the next one, I'm doing 47 minus 56. So when I subtract this, I'm getting negative 9 over 4. So I get negative 2.25. And then for the last one, 56 minus 56 is 0. So I get 0 over 4, which is just 0. You don't need the 2 decimal places there, but you can if you want to. So what we see here is that our first value is 1.5 standard deviations from the mean. So this value occurs to the right of the mean, which means it's larger, which is true, right? 62 is bigger than 56. But it's a usual value. It's still within 2 standard deviations. So when you're talking about your z-scores, we go from -2 to 2. So this is usual. And then beyond that, starts to become unusual. Okay. If you hit 3 or more, then you're very unusual. So this value is totally usual. So 62 miles per hour is normal for that area. Here, our value is negative 2.25. It's negative, so it means that that speed is slower or less than the mean, which makes sense. And it is negative 2.25, so this is unusual because it's outside that -2 to 2 range for our z-scores. So someone traveling only 47 miles per hour would be unusual, right? So that it happens, but not very often. And then for the last one, if someone's traveling exactly 56 miles per hour, the z-score is 0 because it is exactly the mean. It's not bigger or smaller at all. There's no deviation there. So your z-score is 0. So when we're talking z-scores here, so anything in between -2 and 2 is usual. When you go to 3, it is unusual. And beyond 3 is very unusual. And the same thing this way. So if we go down to -3, this is unusual. And if we go past that, this is very unusual. So your z-scores, again, 95% of the time are between -2 and 2. So these are our usual or our normal values. Okay, let's do one last example here. So the table below shows the mean heights and standard deviations for a population of men and a population of women. And we're going to compare the z-scores for a 6-foot-tall man and a 6-foot-tall woman. Assume the distributions of heights are approximately bell-shaped, and they typically are. So heights and weights tend to be bell-shaped. Now we are in inches here. So if we're 6 feet tall, that's 12 inches per foot. So we're looking at a 72-inch mark for our data point. So let's do the men here. And again, my x value here is 72 inches. So I'm going to take my x value, I subtract it with the mean, and I divide it with the standard deviation. And let's see, what do I get here? I get 0.7. For this one, again, I take my 72 and I subtract it with the mean, and I divide it by my standard deviation. And what I get here is about 3.0, so a little bit of rounding there. Let's see, I need to be more exact. So we do get 2.96 instead. So your book rounded to 3.0. We do usually use 2 decimal places for z-scores, so I would probably actually use 2.96 instead, but 3.0 is close enough. So what we see here is that for someone to be 6 feet tall for a men's height, this is very usual, right? So the deviation or the z-score is 0.7, meaning that it's 0.7 standard deviations from the mean. This is within our range of usual values for z-scores. So it would not be unusual to see someone who's 6 foot tall who's a man. Now for women, we get a different value, right? We get about 3 instead. So this is now looking at the very unusual category. So most women are not this tall, right? This value is outside of that -2 to 2 range for a z-score, which contains 97% of all the data for that population. So this is outside this. It's actually right around 3, which is getting to that very unusual mark. So it would be unusual to see a woman who is 6 feet tall. So that's just a little bit about z-scores. And like I said, we're going to be coming back to these a lot later on in further chapters, but they're really nice. It kind of gives us all the same information. So notice that we're really just coming back to this idea of 2 standard deviations. So if data is within 2 standard deviations of the mean, it tends to be very usual. If it's outside those ranges, it tends to be more unusual. So not that doesn't happen, but it's just less likely to be seen, right? There are plenty of women who are 6 feet tall, right? It's not unheard of. It's just not as usual on a day-to-day basis.